este webinar está dividido em duas partes. A primeira eu vou falar rapidamente sobre os produtos da Vortex e como vocês puderem utilizar, fazer uso deles para nos projetos eólicos que você tem, que vocês têm. E depois vai falar Uriel, que ele tem um estudo feito com projetos no Brasil e alguns efeitos térmicos e alguns efeitos, e também a calibração que a gente faz. Então, rapidamente, Vortex o que faz é dados de evento, a gente o que utiliza é o reanálise e melhora a qualidade do reanálise, tanto em resolução como em qualidade, para ter um nível menor de incerteza e incertidumbre. A gente poderia dividir os nossos produtos em duas classificações, uma de mapas, tem mapas de alta resolução e de baixa resolução, e tem os produtos de séries, que são séries horárias ou séries temporais. Então, os mapas que você tem mapas a 1 quilômetro de resolução espacial para fazer prospecção de áreas maiores, onde você está procurando o recurso que você tiver em regiões eh, maiores. Por exemplo, todo o Brasil ou um dos estados em específico. Então, se você estiver fazendo prospecção de áreas, de grandes áreas, você poderia utilizar um Maps que tem o entregável de velocidade mediana, densidade, temperatura, a 1 ou 3 quilômetros de resolução espacial. A gente poderia fazer até 100.000 quilômetros quadrados, e inclusive mais. Depois de alta resolução, a gente tem o farm e o blocks. O farm é um produto de microescala a 100 metros de resolução espacial. Ele tem os valores do vento de uma área. Então, você pode utilizar ele para fazer um layout, você pode fazer a classificação da turbina, você pode fazer também estudos de produção. Mas se você estiver interessado em fazer estudos de produção baseados em horas ou em tempo, você tem o blocos, que ele tem a temporalidade, tem as séries temporais, cada 100 metros da malha, para 30 minutão, para um ano representativo ou um ano calendário que você quiser. Então, esses são os mapas, e para a série você tem a série a 3 quilômetros de resolução espacial, ela está feita para fazer a correlação, se você tiver medições, e extrapolar ao longo prazo. Depois você também tem o Times, que o Times é um produto de microescala a 100 metros de resolução espacial com a série temporal 10 minutos. Então, você tem uma série com valores do vento cada 10 minutos para 10, 20 ou 30 anos. E também pode ter acesso à turbulência, e também agora a gente pode calibrar, ajustar com as suas medições. E depois a gente tem o produto 100% feito com microescala, que é o LES, que ele está feito com Large Shade Simulation. Depois, aqui você pode olhar um resumo dos nossos produtos, do Maps. Você tem grandes áreas eh, regionais, tem o MAS, que é um top 5, tem o LAES, tem as séries, tem o Farm, o Blogs, que é o principal entregável do Farm e do Blogs, é o arquivo WRG, para utilizar eles como um mapa de recurso nos principais softwares da indústria, como pode ser OpenWinch, WinFarmer ou Wincy. E também tem o Times, o Extremes e Icing, que são produtos muito Extremes e Icing são produtos muito mais específicos. O Extremes é produtos do eventos extremos, de eventos extremos, e Icing de heladas. Depois aqui você pode olhar os entregáveis dos diferentes produtos e a resolução que tem elas, junto com os principais entregáveis. Por exemplo, no Blogs você tem o arquivo, a resolução a 100 metros, tem a série temporal 30 minutão, tem até 1.500 quilômetros quadrados e tem os principais outputs do software. Agora eu vou abrir, vou deixar de compartilhar agora a minha tela para compartilhar a interface da Vortex, porque a gente não faz pré-cálculo. Tudo ah, o que a gente faz é feito através da nossa interface. Então, a gente não sei, está olhando a minha tela? Sim.
Sim, sim.
Então, esta é a nossa interface. A gente tem um mapa de 1 quilômetro de resolução espacial de graça. Você pode se cadastrar na nossa interface. Vocês conhecem, se vocês tiverem usuário. Na interface, você pode ter acesso ao mapa. Você pode fazer clique e tem uma roça do vento e tem uma velocidade mediana do recurso eólico para o longo prazo, né? E você poderia selecionar a altura do mapa. Tem a 100, a 150 e a 200 metros de altura, para este mapa que é gratuito. Depois, se você quiser fazer qualquer cálculo, você tem que ir à pestana New e você pode selecionar qualquer dos nossos produtos. Se vocês tiverem perguntas sobre os nossos produtos, vocês agora podem fazer as perguntas na pestana de Q&A. Mas você poderia fazer o cálculo de qualquer dos nossos produtos, por exemplo, do MAST, e você seleciona a área, você poderia fazer upload de um arquivo KMZ, se você tiver, e seleciona a área que você quiser fazer o cálculo. Você tem áreas de até 4.000 quilômetros quadrados. E se você tiver medições, a gente não precisa medições, mas se você fez a campanha de medição e você tiver um ano de medições, a gente poderia fazer a calibração da capa. O produto Farm é feito com o WRF, que é um produto que resolve as equações atmosféricas para representar condições do vento que você tiver na sua área. Então, tem um nível menor de incerteza que o que tiver um produto, um um modelo linear, tá? Então, você poderia calibrar as suas medições, os nossos mapas com as suas medições. Para o lançamento de uma série, por exemplo, você somente precisa coordenada, porque é somente para um ponto, não é uma área, e você tem de graça, você tem 6 meses. Então, você poderia, se você agora mesmo ter acesso à interface. Se você está cadastrado na nossa interface, você pode fazer rolamentos de séries gratuitas de 6 meses. Isso é de graça, mas a gente tem 10, 20, 30 anos. Uma vez eles ficam prontos, a gente tem que fazer o cálculo para você. A gente não tem pré-cálculos, então, uma vez a gente fez o cálculo para vocês, que não ter pré-cálculo, o que facilita é que a gente pode fazer as últimas atualizações do modelo e do reanálises, tá? Isso é uma coisa importante para dizer. Então, uma vez fica pronto o cálculo, você pode se descargar as capas. Você tem todas as variáveis, porque como a gente faz o cálculo 3D, a gente faz a modelagem da toda a área, desde a, a verticalidade e a horizontalidade. Então, você tem todas as alturas, tem todas as variáveis, e todas as alturas você pode se descargar desde a interface. Você pode selecionar single, por exemplo, se você somente quiser uma altura, e você poderia se descargar qualquer das alturas disponíveis, sem custo. Aqui a gente tem as alturas cada 10 metros, mas se você quiser uma altura específica, você poderia selecionar aqui 152, 154, 155, e você selecionar as alturas que vocês quiseram. É, uma coisa importante é que se você faz a calibração, você tem acesso à capa calibrada e ela não calibrada. Então, você tem as duas capas, uma calibrada com as suas medições e uma sem calibrar. Então, assim, você pode olhar as diferenças, né? E se você tiver também uma, uma um layout preliminar, você poderia selecionar as coordenadas e se descarregar um PDF, um pequeno reporte com as coordenadas, a velocidades medianas, os valores de variable e a URF. E também você tem uma tabela de ocorrência com a temperatura, a densidade também, na velocidade mediana a Windows e também tem acesso ao histograma de velocidade com o ajuste de wave. Eu não sei se você perceberam, está aqui, mas eu acho que é a minha tela que não permite fazer, ele está fazendo, mas você só olhando, está aqui, esse, o ajuste de wave e a gente tem, está aqui, né? Então, gente, isso é pela minha parte. Eu não sei se ainda estão assistindo a minha tela. Eu acho que sim. Então, era a minha apresentação, resumindo um pouco dos produtos da Vortex e resumindo um pouco a interface que tem Vortex, ah, que tem Vortex. Eu vou compartilhar agora. Então, vocês, é isso, a última, resumindo um pouco, estes são os nossos produtos. A gente não tem pré-cálculo. Vocês puderem ter acesso às séries gratuitas de 6 meses e fazer um teste, se vocês quiseram. A gente vai estar na Brasil Wind Power, então a gente poderia conversar lá e se vocês estiverem interessados, a gente poderia fazer um teste dos outros produtos. Agora eu vou dar passo a Uriol. Ele vai compartilhar sobre os temas térmicos que ele encontrou em Brasil com um estudo que ele fez. Ele tem validado muitos destes estudos e destas capas e ele vai falar um pouquinho disso, tá? Mas ele não fala português, então agora we will start speaking English. Mas se vocês tiverem alguma dúvida, a gente pode dar resposta a ela na secção da Q&Answers, tá? Uriol.
Muito obrigado. Sorry, my English is, my Português is muito ruim. So I will do the presentation in English, okay? So I want to make this presentation about what is a wind map or a wind spatial distribution, and present you some very quick two cases that I think are very interesting for the Brazilian market and Brazilian country. And later, very briefly, I will present the calibration, okay? How we make the calibration of wind area, okay? So the spatial wind speed distribution is we can call it different ways. The wind resource of an area, the wind map, the wind field. Okay. What we know for an area when we are interested in the wind is that the wind will change across the area, okay, and every site will be different, and the way that the wind changes will be different, okay. So the spatial wind speed distribution, okay, we can set a definition, for example, the variation of wind speeds across different locations within a specific area, okay. So how we can compute a spatial wind speed distribution or a wind map? There are different methods. You may know them, but let's make a recap of them. First method, it's by making an horizontal extrapolation given a time series inside the area we are interested in. So we just have the roughness, the topography, and a time series in that area, and we make an horizontal extrapolation just to set this information into all the area we are interested. Another method is the CFD models, which they account for the fluid dynamics. They consider the wind as a fluid, and by the typical computational fluid dynamics equations, they try to set up how that fluid, in this case the wind, will move around the area for influenced by the topography and roughness. Okay, and the other way to computing, or in this list, it's by using meteorological models. In our case, we use work model, and what they do, it's a process we call downscaling, because we start with low resolution data, and we run work to make a much higher resolution and detailed information on the atmosphere. Okay. So just to show some differences that you may have when using different data, which comes from different models. Okay, I want to show a special case where you can easily see that how different models have different behaviors. So, for example, one phenomena that you all may know, okay, it's in a hot day, okay, you detect the sea breeze, okay, it's very hot, you go to the beach, you lay down, and you feel like a colder wind coming from the sea. Okay, this wind comes from the sea, which is colder, to the warmer area, which is inland. Okay, and this makes the hot air move vertically, okay, and creates a circulation, okay, that we call the sea breeze. Okay, this is a kind of wind that's totally driven by the changes in temperature. If we do not consider temperature in our wind computation, this effect, for example, will not be considered. Okay, so let me show you a sea breeze influence in a case study. Okay, it's a place where we have, this is the domain of the simulation. This is where we run our simulations, and we have a sea on the northeast and land the rest of the area, but you can see on the southwest that there is much complex topography. Okay, and then we run two models. Okay, the first one is WASP, which would fit into the group A that I presented before, which is the model that takes a time series and then tries to extrapolate that information into the rest of the area. In this case, we introduced a time series in the center of the domain, and then the model extrapolated the information. Okay, giving a pretty soft wind flow, well, with some variations on shadows on the highest or the more complex terrain areas. And then we repeated the process, but in this case the model was worked on our typical Vortex farm, and this is what we got. Okay, this is the same area, same place, same height at 100 meters, same scale. Okay, and what we see here, it's the most windy part is the near the ocean, okay, near the sea, and it's very different the area that's more near to the sea. So we can see that in this case the model has at least make some sea land wind, and shows us that both models produce very different patterns. Okay. So in this case, model plays a crucial role, okay, but also the resolution, okay. Having higher resolution lets you capture even better this kind of very particular effects. Okay, let me present another case. Okay, in this case, it's not a sea breeze, but it's a case where in many for many time and many places, lots of projects were in complex topography sites. You would expect that on higher places of the terrain there would be high wind speed, and on lower places there would be at least more or less few wind. Okay, so I will present a place where this is not true, and it's been checked with measurements. Okay, and it's located in Brazil. Okay. Uh, the topography, uh, it's here in the center. The hard brown, it's higher places, and the lighter brown, it's lower places. Okay, you have a ridge on the southeast side that covers all the area on the south, and then you have some hills located around. Okay, and then let's do the same experiment with WASP, same way, zero in the center, and see how this which wind field it generates. Okay, you see that there are high wind speeds on the higher areas, especially on the southeast. And then there are other high wind speeds on some hills here on the northeast, and then some places where with higher wind speeds, but you see that mostly it tells you that the higher wind speeds are on the higher places of topography. Then let's check what Vortex Warp at 100-meter resolution produces, and we see a totally different pattern. It extends the high wind speeds on the west with larger areas, not being just restricted to small hills, but extended. And the most relevant effect that I would like to show is that on the east side, okay, that's where the highest mountains are. There are not the high wind speeds in this case. Okay, we see a very soft wind that's increasing from east to the west. Okay, with a higher wind speed generating with big areas here, not just these very small areas here. So we can see, okay, the key is that we see very different patterns. So it tells us that okay, the maximum wind speeds do not correspond with the maximum elevation. Okay, so something's going on here. Okay, so using the WRF model, I tried to make two graphs to take a deeper look or more detail on the phenomena. And this is a graph of the temperature variation with height, okay, across the different areas, which goes from west to the right. Okay, imagine I make a cut from the west to the east. Okay, like here. Okay, how you can see my point. Okay, my pointer, and that's what we see here. Okay, the on the gray area, it's the topography, the mountains. Okay, and the colored one is the values of temperature at different heights. Okay, above the surface of the topography. So the wind mostly comes from the east or near east directions and moves free. So as we would ideally think and said, is that the temperature decreases linearly with the height. Okay, so we see the lines of temperature are totally horizontal. So, but this, as the wind flow moves from east to west, it crosses the mountains, which makes some perturbance on it, and alters the wind flow and the atmosphere. Okay, this in this case produces a change in temperature that is not expected with an increase. Okay, we see like temperature mountains. Okay, that moves not only on the lower heights, but up to the altitudes above what 1500 meters. Okay, this is well, this is mostly produced by the phone effect. Okay, And but we see that the model, the key thing here to consider is that the model is capturing some temperature alteration. Okay, so as we saw before, if the temperature is modified, it can produce some alterations also in wind. That's what we are particularly interested in. Okay, so let's see the same graph. Okay, but now let's picture the wind speed. Okay, uh, the same way we have the maximum wind speeds are reds or and dark reds, and the lower wind speeds are blues and greens. Okay, so the same way the wind looks pretty smooth, pretty increasing increasing linearly in with height on the east side, while as it moves through the mountains to the west, okay, it's being perturbed. Okay, it's been altered, and we see the maximum wind speed as we saw on the map before for Wharf, not located on the peaks of the mountains, but on the leeward area. Okay, we see the most windy areas here, okay, on the leeward area, while later on the valley decreasing again. Okay, so we see that the model is capturing some kind of effect which alters wind speed and temperature in abnormal way if compared to the other models. Okay, so now that we have discrepancies between models, we can set up our own strategy to basically two objectives. Okay, the first is to check if this phenomena is occurring or is an hallucination of some of the models, and the other is quantify it. In case some of the model is correct, then quantify this variation. Okay, so for this we would need at least two medmasts. Okay, we would locate one medmast, for example, on the top of the hill on the east, and then the other on the west on another expected highest wind speeds for one model. Okay, the objective is for this is to select one model, okay, and then to quantify the accuracy and be able to calibrate later on the model correctly. Okay, so we've seen everything here, all the wind spatial distributions in a qualitative way, but we need to quantify it. Okay, we need to quantify in order to compare models, okay, with a methodology, and also to validate models against some measurements in case we have them. Okay, so we would need at least two medmasts. I set up an example of three medmasts. Okay, imagine in the case of a breeze case, we have three medmasts, A, B, and C. Okay, so we compute what we call speedups. Okay, speedups is just a factor. So we would compute the mean wind speed at point A versus the same at point B, and we would repeat for points A and C. And then we would repeat this for a model, would repeat for another, and in case we have a medmass, we would compute that for the medmass location. Okay, this way we would end up for a value for each pair we have, and we could compare the models one against another with a number. Okay, we could set up in our methodology and compare that numbers. Okay, and then if we have the medmass, we could validate. Okay, so here we are not validating, okay, wind speeds, we are validating spatial distributions. Okay, this is the objective of using speedups. Okay, uh, so imagine now you want to fix your map. You say in one place, you know your bias, you have a measurement, you have your model. You can increase or decrease that wall area, okay, and you would fit the map to match exactly your measurements, okay. But in that case, you would not correct the wind spatial distribution. Okay, this is another example where you can see the difference of when your objective is to determine the wind speed at a single location, or you want to measure how accurate is a spatial distribution. Okay, so let me present now the calibration with measurements that we perform at Vortex. Andre commented out more or less that we can do that for farms. Okay, we can do that for blocks too. Okay, farm and blocks are use the same technology. Okay, we run the simulations for an area at 100-meter resolution. Okay, but for blocks we save the simulation after it's finished with at fixed heights. Okay, not all the atmosphere, but heights up to 300 meters, and for all the area, and then you can perform as many calibrations as you need and extract time series. And for farm, we just don't save the simulations, but we save the VRG files and GIS files to extract the temperature and all the variables. Okay, and but you are here, you are still able to calibrate the farm if you upload the data prior to running the simulation. Okay, but in any case, both can be calibrated. Okay, with in which case you will end up with having the raw model output and the calibrated output. Okay, so let me explain very quick how the calibration works. Okay, we need the simulation. Okay, we need at least one landmass with 1 year, and with that inputs, first step is we calibrate the time series of the simulation using your landmass. So we end up with a calibrated time series, which has the wind direction, histogram, so A and K and other parameters corrected, not only the bias, but all the time series, because we calibrate each timestamp. Okay, and then we try to expand that information from the medmass location or multiple medmass locations to the rest of the area. Okay, so we try to adjust based on the similarity of the medmass location to the rest of the areas. So we try to figure out based on topography or correlation from the medmass to the rest of the points how similar they are, and this helps us to introduce how the information we have from the medmass is reliable or not to each point in the area. Okay. So by adjusting time series first, we can correct histograms, wind directions, and not only the mean wind speed. Okay, and with the inclusion of the similarity, we correct the speed ups. Okay, and we prevent mostly the creation of bubbles in data. So we do not want to destroy the spatial wind distribution. Okay. Uh, the accuracy of this method improves with the availability of more medmass, as we consider that having more medmass, we have different wind patterns, so we can use different kinds of information to correct different areas in the map. Okay, and this is more or less about the calibration. And just to end up, okay, let me make a summary. That I want to show you that the first point was that the wind speed spatial distribution and bias, they have different accuracies. There are different targets. Okay. Second is that different models can produce different results. Okay. In terms of bias, okay, but also in terms of spatial distribution. Okay. And the third, okay, is that the model spatial fields, okay, the wind maps can be improved. Okay. And if you make a good design of your MedMass campaigns, okay, that helps you later also improve more your wind maps. Okay, and that can be performed if you are using a correct calibration method. And that's all. I hope it was at least a little bit interesting. And maybe now we have Patricia, Andre, some questions and answers.
We have still 5 minutes left. Andre, maybe you can read this question in Portuguese. Well, I understand, but
Yeah,
you,
Uriel, this one you can answer. This question you can answer. Just to make a quick comment about what Uriel comment and what Uriel said. This is important to understand that the thermal effects and some of the effects that do not have to be influenced by the topography. Like it's a common thing with when you are dealing
Yeah,
with ocean effects and with
yeah.
sea effects, are not characterized but by the linear models. So it's pretty common to use in Brazil when you have the measurements and you did the measuring campaign to do the horizontal extrapolation with the measurements, but and to think that that is accurate because you have the measurements, and since you have measurements, then extrapolating and getting an area based on the measurements that will be with a low uncertainty. But the
Mhm.
thing is that when you're extrapolating that,
Mhm.
you could be not characterizing those thermal effects. So that's when it's important to use modelization that takes into account all the variables of the atmosphere, like Uriol was explaining. So a really good combination will be the measurements, the and a worse modelization bring together to reduce the uncertainty. So the question that you have, Uriol, is si é possível escolher o método de calibração das torres ou é uma metodologia própria da Vortex? Eu acho que é muito fácil dar resposta a esta pergunta, porque a gente tem uma metodologia de calibração que a gente tem validada e é a tecnologia que é disponível na interface para fazer de graça. Não tem um custo adicional para fazer esta calibração e você pode fazer. Mas é uma metodologia da Vortex. Não pode escolher outras metodologias de calibrações, como outras que há. Verdade, Uriel?
Yes, yes, that's true. We have our methodology, and then you cannot choose between different methodologies. The thing you can do is you can do two things. First is compare the calibrated layers with non-calibrated, and then check what the calibration has done or the changes it has done. And the other thing you can do is if you have multiple medmasts, you can reserve one of those medmasts or any medmast you want to reserve. Do not include them in the calibration, and later you can validate the calibration. Okay,
É
but yeah.
outra coisa que é importante, que você pode fazer a calibração com as torres que você quiser. Se você tem uma torre, você pode fazer a calibração. Mas se você tiver 10, se você tiver 5 torres a diferentes alturas, a gente poderia fazer a calibração sempre. E a gente poderia fazer a calibração com todas as torres que você tiver dentro da área. É, e, Uriol, a gente tem outra pergunta, que é, a turbulência foi avaliada também, que se um, if we validated the turbulência, e se there was houve um aumento nas regiões de aumento de velocidade. E,
In the case of blocks and farms, the resolution, especially the temporal resolution, is not high enough to use the temporal turbulence because it's not accurate enough. You need at least 10 minutes of data to get reliable turbulence. Anyway, for example, in the case that we saw that there was a high wind increase in the leeward area, we know that in that area there was a very high vertical wind. Okay, so we know that a lot of turbulence will be occurring, especially on typically on all leeward areas. So in that case, blocks would tell you that there's turbulence because you can plot and extract turbulence map, and the average will be pretty accurate. Okay, you will see what's the average turbulence in that area. But if you want to move in bigger detail and get the time series of turbulence, that then you will need
at
further plot
times.
that time series at terminal resolution, and especially design with a model that computes the turbulence some turbulence equations.
Actually, we have validated the turbulence in our validation of times. We validated more than 200 sizes, and some of them we validated the turbulence. Times is our new products, is a long-term 10-minute time for solutions. And you have the turbulence in that series, and actually is the product we recommend to be used when you want to analyze the turbulence. And normally our clients buy together the farm or the blocks and a time series. In this case, the time series will be times. We also have Uriol another question. It says, I would like to know how Vortex deal with nocturnal effects, low-level jets, nocturnal low-level jets from the modeling side. You're muted.
Okay, this is the same thing. Okay, the low level jets, for example, we need to have a big domain, okay, and a high resolution simulation, because the changes in wind speed with the altitude are big, so you need a high resolution. So the same way we are detecting some effects that are driven by temperature changes. In this case, we need the reanalysis or data that we are simulating to provide some indications that these precursors of the low-level jets are in it. In those cases, we've detected some low-level jets effects, for example, in Egypt, for example. I remember that we had a vertical inverted shear profile during nights that was very high. Okay, and then during the day there was the thermal effect from the sea. So in that places, yeah, we had two big effects, one during the night and the other during the day.
I don't know if we have more questions. I don't see if we have no more questions. So I think we can, well, we're up time. It's 15. As que eu acho que a gente, se vocês tiverem outra pergunta que vocês quiserem fazer, a gente pode dar resposta a ela no e-mail. Vocês poderiam enviar um e-mail a mim, ou a Patrícia, ou ao Uriol, e a gente vai dar resposta às dúvidas que vocês tiveram sobre esta apresentação ou outros produtos da Vortex. Uma coisa importante é que a gente vai estar na Brasil Wind Power e a gente poderia agendar reuniões presenciais. Vamos estar Uriol e eu. Vamos estar lá e a gente poderia comentar mais detalhadamente esta apresentação que a gente fez, e também temos algumas entradas de graça para os assistentes que se vocês quiserem assistir. Muito obrigado pelo tempo. Thank you, and I hope this webinar was useful for your business and your projects.
Yeah, thank you. I'm very happy to attend Brazil too. My first time there, so if you come by our booth, it will be really great to talk to you. Okay,
Ciao,
thanks.
ciao, ciao.
Thank you very much.